Welcome, curious minds, to the deep dive. Today, we're embarking on an exploration that genuinely bridges some huge fields. AI, neuroscience, physics, even philosophy.
Yeah, it's a really big picture kind of thing.
We're going to delve into this, well, really audacious idea that the universe itself, its very fabric, might be inherently computable.
It's a fascinating convergence, definitely. And our deep dive today, it's built around insights from an article looking at the Lex Fridman podcast featuring Demis Hassabis, the co-founder, CEO of Google DeepMind.
Right, the DeepMind guy.
Exactly. And we're really going to be digging into his boldest ideas, his conjectures about what machines can actually learn.
Okay, so our mission then for this deep dive is to unpack this central thesis from Hassabis. It sounds honestly pretty provocative.
It is.
That the secrets of nature, the really deep stuff, are inherently learnable, but specifically by classical machines. What does that actually mean for, intelligence, the universe, maybe even the AI we have right now? That's what we're trying to figure out.
Okay, so the absolute heart of his argument, it's this profound conjecture he talked about during his Nobel Prize lecture.
Oh, wow. Okay.
He stated, and this is really the core idea we need to grasp, any pattern that can be generated or found in nature can be efficiently discovered and modeled by a classical learning algorithm.
Hold on. It's huge. Any pattern.
Yeah.
And efficiently.
Yeah.
By a classical learning algorithm.
Yep.
So when he says classical, he means what? Like the neural networks we have now.
Yeah.
Not quantum computers or some sci-fi tech.
Exactly right. Classical non-quantum neural nets, the deep learning models that are, actually being deployed. He's giving them this incredible, almost unexpected power.
It's not just a technical claim then, is it? It sounds almost philosophical.
It absolutely is. It's a deep statement about the fundamental structure of reality. It implies something about how understandable the universe actually is.
How so?
Well, think about it. If reality itself is structured in a way that kind of prefers patterns that are learnable, it suggests the universe is inherently comprehensible, at least by certain kinds of intelligence, like nature might have a built-in cheat sheet that AI can read.
A cheat sheet for AI. Huh. Okay. And this really comes into focus when we look at problems that used to seem, well, almost impossible, right? Like nonlinear dynamical systems.
Exactly. Classical computing has always, really struggled with those.
Things like long-range weather forecasting or fluid dynamics, stuff governed by those crazy complex equations like Navier-Stokes. Why are they so hard?
They're incredibly tough because tiny, tiny changes at the start, they can lead to completely different outcomes down the line. Wildly unpredictable.
The butterfly effect kind of thing.
Precisely. It's like trying to predict exactly where every single drop of water in a raging river will end up minutes later. But here's the compelling part. Deep learning models, they're making astonishing breakthroughs.
How?
Well, take video generation AIs, like Google's Veo, for example. They can model complex fluid dynamics pretty convincingly.
Right. I've seen demos. The water, the smoke.
Yeah.
It looks real.
It does. And the really striking thing is how they do it. They're learning it, apparently, just from visual observations, meaning watching tons of YouTube videos, basically. They don't need direct physical simulations run inside them. They don't have the explicit equations programmed in. They just watch.
Whoa. So the AI is figuring out the underlying physics just by looking at pixels. That seems like a massive leap.
It is. It suggests AI can infer these hidden underlying structures. Hassabis talks about low-dimensional manifolds.
Okay, you lost me a bit there. Low-dimensional manifolds. Can you break that down?
Sure. Imagine a crumpled piece of paper.
Right.
It looks incredibly complex, random folds, creases everywhere.
Yeah, nice.
If you tried to describe the exact 3D position of every single point on that crumpled ball, it's a huge, messy, high-dimensional problem.
Yeah.
But the AI isn't necessarily doing that. It sort of realizes, this complex thing is actually just a simple, flat, two-dimensional sheet that's been crumpled up.
Okay. So it finds the simpler reality hidden inside the complex appearance.
Exactly. It's identifying the essential underlying structure within what looks like high-dimensional chaos. And that lets it predict the behavior much more efficiently. It finds the flat sheet within the crumpled ball of data.
That crumpled paper analogy actually really helps.
Okay.
And we see the same principle, finding hidden order in massive complexity with things like AlphaFold and AlphaGo too.
Absolutely. Both operate in these incredibly high-dimensional spaces, but they found the structure.
AlphaFold. That was the protein folding one, right?
Yes, exactly. A huge breakthrough.
Yeah.
Predicting how proteins fold was considered, well, computationally intractable for ages, the number of possible ways a protein could fold is just astronomically massive.
Well, impossibly huge.
Yeah, it seemed way beyond calculation for humans or machines.
And similarly, AlphaGo cracked the game of Go, another domain with just insane complexity.
Right, more possible moves than atoms in the universe, that old chestnut.
Yeah.
But it's true, the complexity is staggering.
So what's the connection? What's the shared insight from AlphaFold and AlphaGo? How does they pull it off?
The key insight, really, is that both systems learned structured models of their environments. They didn't just brute force calculate everything.
So they didn't check every single possible protein fold or Go move.
No way, that's impossible. Instead, they learned let's call it the inherent logic or the underlying landscape of the problem, the rules of the game for protein folding, or for Go strategy.
Right.
This allowed them to do an intelligent search. They could focus on promising paths, prune away the useless ones. It dramatically cuts down the complexity, making prediction and finding good solutions actually manageable.
So this ability of AI to find the hidden structure, like with the fluids that AlphaFold, AlphaGo, that brings Hassabis to this bigger idea about why nature itself might be so learnable, his concept of survival of the stablest.
Precisely. It's like he's extending Darwin's idea, but into physics and cosmology.
Survival of the fittest, but for physical patterns.
Kind of, yeah. The idea is that nature, through processes like biological evolution, sure, but also geological weathering, or even the stable orbits of planets, it naturally selects for stable, enduring structures and configurations.
Things that last.
Things that last. And because these patterns are stable and enduring, they have an inherent order. Hassabis argues this makes them inherently learnable by AI.
As opposed to
something completely random and unstable, like, say, trying to factor a massive number that was generated randomly. There's no inherent enduring structure there to learn from. Nature's patterns, though, the ones that persist, they have that structure. They're modelable.
That's a really neat distinction. Okay, so this thinking leads him to propose something quite formal, right? A new class in computer science theory. LNS.
Yes, LNS, Learnable Natural Systems. He's proposing this as a theoretical category.
And what would fit in that category?
It would specifically include these physical systems with structure. Problems that are complex, yes, but ultimately learnable efficiently by classical neural networks.
And this would distinguish them from, well, the really hard problems in computer science.
Exactly. It sets them apart from abstract, presumably intractable problems like factoring huge integers, which, lack that kind of stable physical grounding or structure.
This whole perspective, it also seems to connect with a growing idea in physics, doesn't it? That information might be more fundamental than even energy or matter.
It definitely aligns with that view. Hassabis seems to lean into this idea that information is the bedrock.
And if information is the fundamental thing, that changes how we think about computation, right?
It really does, because if information is fundamental, then classic computational problems like P versus NP, they stop being just abstract math puzzles.
P versus NP, refresh my memory, easy to check answers versus easy to find them.
That's the one. Are problems whose solutions are easy to verify also inherently easy to solve? If nature itself is efficiently solving problems that look like they belong to the NP class, like protein folding, finding that one right structure out of zillions,
then computation should be able to as well, by sort of tapping into how nature does it.
That seems to be the implication Hassabis is exploring. If nature finds efficient solutions, maybe our algorithms can learn to mimic that efficiency by understanding the underlying informational structure.
What's really striking about all this, and Demis really emphasizes it, is how many people thought solving protein folding or mastering Go would absolutely require quantum computers.
Oh, definitely. That was a common prediction. The complexities seemed just too vast for classical machines.
And yet, DeepMind did it with classical hardware using deep learning. That's the real shocker here, isn't it? We might just be massively underestimating what these classical neural nets can actually do.
I think that's a huge part of his message, absolutely. Look at the examples piling up. AlphaFold 3, mapping genetic codes directly to protein functions. That's incredible.
Or AlphaGenome, exploring genetic expression super efficiently.
Right. And even back to those video models we talked about, simulating physics, lighting, reflections, without being explicitly programmed with the laws of physics.
So what's the common thread? Why are they so good at this?
Well, it seems neural networks are just exceptionally good at finding the downhill slope, the gradient, in these enormous high-dimensional landscapes of data.
Like a super sensitive compass finding the easiest path down a mountain.
That's a good way to put it. They can sense the optimal direction even when the terrain looks impossibly complex to us. They turn what seems like chaotic, insurmountable problems into, well, tractable modeling challenges by finding those hidden gradients, those underlying structures.
And this connects to that idea of emergence too, right? Where you have simple rules, but they generate incredibly complex results, like cellular automata.
Exactly. Simple rules, but the patterns they create can be mind-bogglingly complex, sometimes looking almost random, sometimes highly structured.
But even those complex emergent systems,
Yeah.
Hassabis seems to think most are still modelable by classical machines.
That seems to be the suggestion, yeah. That even emergent complexity often retains enough structure to be learned. However, this does raise the question of limits.
Right. Are there things that are just too complex?
Well, maybe. Think about truly chaotic systems. The ones that are hypersensitive to initial conditions. The butterfly flapping its wings causing a typhoon half a world away.
Can AI model that?
That might be the boundary. Systems where tiny fluctuations get amplified so extremely, their sheer unpredictability might put them beyond the reach of even the best predictive models, AI or otherwise. There might be an inherent limit to learnability there.
So ultimately, Hassabis isn't just seeing AGI, artificial general intelligence, as like an engineering problem to solve.
Yeah.
Build a smarter machine.
No, it's much bigger than that for him.
He sees it as a tool, a fundamental tool for science.
A profound tool, yeah. A tool to help us answer the absolute deepest scientific and philosophical questions we have about the universe.
It really reframes the whole AGI quest, doesn't it?
It really does. It shifts the focus. It's not just about building intelligence, it's about using that intelligence to understand reality itself.
We're talking about using AGI to probe huge questions. Can we actually model all of nature computationally? How far can these classical learning methods really take us? Where is that ultimate boundary between what's learnable and what's just fundamentally unknowable about our cosmos?
Exactly. It's both humbling and incredibly exciting when you think about it that way.
So, as we kind of wrap up this deep dive, the picture Hassabis paints is really one where intelligence, nature, computation, they aren't separate things. They're different facets of the same underlying reality built on patterns and structures.
Yeah, different expressions of learnable information, perhaps. And it definitely makes you reconsider the power of classical systems. We might be, vastly underestimating what's achievable right here, right now, without waiting for quantum breakthroughs.
It pushes the boundaries of what we thought was possible, computationally speaking, within this universe. And maybe that leaves us, and you listening, with a final thought to chew on. If AI can really help us decode nature's deepest secrets like this, what new fundamental laws might it help us uncover? Things we haven't even conceived of yet.
And maybe even how does that change our own understanding of our place within this newly understood, perhaps fully learnable cosmos?
Big questions to ponder.